our next stop is functions. And so we're going to get on the same page with terminology and make sure that we have the same understanding regarding what we can do with functions and how to describe them. So first, let's define a function in general. So we have a function f, and it's a mapping that takes us from one set to another. And so we have a function that takes us from a set A to a set B. It maps us from A to B. And what it does is it's going to assign any input value that we take from our initial set A a unique output value in the set B. And this unique value that is assigned to A is denoted f of A. So we say that f maps A to f of A. It maps A to B. We say that f maps A to f of A. It applies a function that takes a value from our initial set and a unique output value is defined based on that input A, and it takes it from A to f of A. So we'll see what that looks like. There are a lot of functions that you'll make use of, especially in programming. For instance, not. When we get into logic, we're going to talk about something being not something else. So what does it mean? If we say that it is raining, raining is equal to true, right? If we say it's not raining, that means raining is equal to false, right? It's not raining. And so what it does is it's a function that takes true to false and false to true. If something is false and you are not that, then the opposite of that is that it's true. So let's look at a function that everybody has seen before, and that is the square function. If we want to square something, we want to map x to x squared. What we do is we apply a function, and we'll call that function square. And it's going to go, we're allowed to square any number within the reals, and so we're going to map from the reals to the reals. So what we're saying is this function takes any input from the real numbers, the set of real numbers, and it's going to output x squared, which will also be a real number. For instance, we can square the number 7, and what we get is we take the 7 as input, and we're going to output 49 because 7 squared is 49. And this is a mapping x to x squared, x to square of x. We can also define a triple function, and this is just a function that's going to take in any real number and return a real number that is 3 times that initial real number. So we'll define that as triple of x is equal to 3 times x. It's fairly straightforward. We're going to take as input some value x, and we're going to output 3 times x. So for example, if we take triple of 7, it's going to return 3 times 7, or 21. And this again is a mapping, and it's taking x to triple of x, where in this case we can also represent that as 3 times x. What about an average function? So far we've looked at examples where the function that we're applying is only applied to one value. There are times that we want to apply functions that apply to more than one value, input value. It's likely that you've only seen functions up until now, or thought of functions up until now, that apply to one input value. But there are many times where we need more. For example, if you wanted to create an average function, or something that takes an average of 2 numbers, the hint is in the average of 2 numbers, right? We need both of those numbers in order to know what we're taking the average of. So for instance, I have an average function, and it's going to go from reals cross reals, which is the Cartesian plane. I'm going from r squared to r. And what that means is I'm going to take in two values, say x and y, but I'm only going to return one. And that one value that I'm returning is going to be the average of x and y. So in this case, it's defined as, we're going to take in as input two input values, x and y, and I'm going to take them in as an ordered pair. And the reason that doesn't exactly matter for average, but I'll talk in a second about why that order can matter. So in this case, what we're going to return is a number, which is the average of those two, x plus y divided by 2. Okay, so that's our return value. And so even though I needed those two input values, I'm only returning one number, which is x plus y over 2. And in this scenario, what I would get if I have, for example, the average of 5, 7, I'm going to get 5 plus 7 over 2, or 12 over 2, which is 6. Okay, this is great, except what you'll see here is that sometimes we don't include those angled brackets. And that's when it's implied that you're taking this ordering. Sometimes we just don't include that detail. And to be honest, it's a notational laziness. In this class, I'll try to always be very specific with that notation, but it's fair warning that in real life, you'll see it written sometimes as 5, 7, and they'll assume that that ordering holds. So what this is doing is, again, it's a mapping, but this time it's a mapping from a pair to a single number, which is found by taking the average of x, y. Other ways that we see within computer science the use of functions, there are many, and we'll come to that at the end. But here's an example of a function that's defined to be a type of compression. So this is an example of a type of lossy compression. So here's a function, compress, that's going to take numbers from the set 0 to 255 inclusive, and it's going to return one of 5 different numbers. So you can see in this set, there are only 5 numbers. On the left side, the starting side, there are 256 numbers. So that is a lot of numbers. So in fact, in order to represent the numbers 0 to 255 in binary, which behind the scenes the computer is storing this information as a sequence of zeros and ones, that's going to take 8 bits. Well, 8 bits takes up a byte. And so then it requires 1 byte, even in grayscale. So this is just one color. Even in grayscale, it takes up 1 byte for every pixel worth of information. This is a challenge. 3 bytes if it's in color, so you can store the red, the green, and the blue. So this becomes a challenge because files become very big, and sometimes we don't care about keeping that quality. And so the way that we handle that is we compress that information. We say, if we have 0 on the left and 255 on the right, do I need to see every possible color within that realm, or is it okay if I approximate a little bit? We have these 256 options that we could choose from. So starting from black and then getting lighter and lighter and lighter incrementally 256 times until we get to white. So there's 254 steps between black and white. And what we do in this process of compression is we say, in this example, we're taking 5 big chunks, so this being the first, and we just say, do you know what? I don't really care in let me get a different pen color. I don't really care in this realm right here if if I'm quite as black as 0, or I'm quite as light as 51, but I'm just going to take an average in there. I'm going to take something roughly in the middle of that at 26. I'm going to say that's good enough for me. And that's everything that is sent to me that's a color between 0 and 51. I'm just going to map that to 26. And the same can be done at the next interval. We can say, well, if it's somewhere between 52 and 103, I'm just going to treat that as 78, and that's okay. And I won't have the same smoothness maybe in my image, but the fact that I can store only 5 possible bins of information is going to save me a lot of space. And so that's more important to me, and I'm going to weigh that. So instead of having a smooth gradation from white to black or black to white, what you're creating is something like bins. And we're just saying it's close enough. Everything that's, between here and here, I'm just going to call that this kind of lighter gray, and so on and so forth. And so this is an example with many more bins, but you can decide, how much you want to compress that data by deciding how many bins you want to break it into. If you need a little bit more information, you don't want to lose too much, but you want to save a little bit of space, you could decide to break it into more bins. And so these are some interesting ways that we can make use of functions.
Where are we going with these functions anyway?
Funny you should ask. Next time we'll talk about domains and codomains, where we look at how a function maps elements from the domain to the codomain.
So the domain is like the start line, and the codomain is like the finish line.
That could not be summed up any better.
See you next time.